You already know how to plot points with x and y. And you know complex numbers. What if I told you these two ideas are secretly the same thing? Start with a familiar Cartesian grid and a point P at 3, 4. Instead of saying how far right and how far up, we can describe this point by its distance from the origin, r equals 5, and the angle from the positive x-axis theta, about 53 degrees. The conversion formulas are straightforward: x equals or cosine theta, y equals or sine theta. And going back, r is the square root of x squared plus y squared, theta is arctan of y over x. This is the polar coordinate system. Same point, different description. Now here's the key insight. Plot the complex number z equals 3 plus 4i on the plane. The real part is the x-coordinate, the imaginary part is y. This is the exact same picture as polar coordinates. Write z as x plus iy, substitute the polar formulas, r cosine theta plus I r sine theta. Factor out r. And by Euler's formula, cosine theta plus I sine theta equals e to the I theta. So z equals or times e to the I theta. Every complex number has a modulus r, the distance, and an argument theta, the angle. The polar form of a complex number is polar coordinates. Three representations of the same point: Cartesian, complex exponential, and polar. Here is where polar form becomes magical. Take z1 equals 2e to the I pi over 6, that's magnitude 2 at 30 degrees, and z2 equals 3e to the I pi over 4, magnitude 3 at 45 degrees. What happens when we multiply them? The magnitudes multiply, 2 times 3 equals 6. The angles add, 30 plus 45 equals 75 degrees. That's the product, and that's all there is to it. In Cartesian form, the same multiplication requires expanding and collecting terms, messy. Polar form turns multiplication into something geometric and obvious. The bridge between these two worlds is Euler's formula, e to the I theta equals cosine theta plus I sine theta. As theta sweeps from 0 to 2 pi, e to the I theta traces the unit circle. The x-coordinate is cosine theta, the y-coordinate is sine theta. At theta equals pi, we land at -1. This gives the famous Euler's identity, e to the I pi plus 1 equals 0, connecting 5 fundamental constants in one equation. Polar coordinates don't just simplify complex arithmetic, they reveal curves that are nearly impossible to describe in Cartesian form. R equals sine of 3 theta draws a three-petal rose, with theta from 0 to pi. R equals 1 plus cosine theta draws a heart-like shape called a cardioid. Theta can be any real number. And R equals e to the 0.2 theta draws a logarithmic spiral, the shape of galaxies and seashells. Again, theta ranges over all rails. Cartesian coordinates make addition easy. Polar coordinates make curves natural. And complex numbers make multiplication geometric. They are three languages for the same plane, and switching between them is a superpower.